evidence of creep and large earthquakes in paleoseismic trenches along the central creeping section of the San Andreas Fault, which sits between the last two major earthquakes, the 1906 San Francisco event and the 1857 Fort Tejon event. Importantly, this creeping section and Parkfield appears to have been the site of two moderate magnitude earthquake foreshocks, which occurred at dawn and sunrise prior to the 8:24 a.m. rupture on January 9th, 1857, which begs the question of how important Parkfield and other creeping section earthquakes may be in larger ruptures like 1857. We know from the occurrence of events across Earth over the past decades, and we certainly have seen that large and complex ruptures do occur. So perhaps it's not surprising that modeling efforts such as USURF-3 have relaxed segmentation quite a bit. And the image on the left is a supplemental figure from USURF, which shows the participation recurrence rate for other faults in rupture along with Parkfield. And out of this comes the potential in a modeling sense for massive earthquakes. So whole San Andreas Fault ruptures, 150,000 year long recurrence, a 2,500 year recurrence for ruptures involving parts of both the north and southern San Andreas Fault in addition to Parkfield. Let me just say that preparing for an earthquake which ruptures both northern and southern California in one go in the same time would be a very different and challenging hazard response for society. And so this is an important question to address. What does science other than paleoseismologic trenching suggest? Slip budget analyses near the northern terminus of the 1857 event and into Parkfield shows that with time, slip experience from creep over the historical period and the moderate magnitude earthquakes that have occurred does not quite keep up with what we presume is the long-term slip rate. And thus there may be a slip deficit developing over time. And today it may be at or exceeding 1 meter in parts of the creeping section of the San Andreas Fault. Paleoseismology elsewhere in Central California, such as the Hayward Fault, shows us evidence for large earthquakes through those studies, in addition to fault surface creep. And importantly, recent studies by Kofi et al. Shows that there's clear evidence of frictional heating from large earthquakes on some traces of the San Andreas Fault at depth within the SAFOD drill cores. So this study suggests that the rupture has occurred through this region. Unfortunately, can't tell us how frequently, only that probably there was displacements of greater than 1 meter and maybe up to 3 meters sometime during probably the Quaternary period. So it seems like we kind of know that big earthquakes must happen, but we still don't know how often and how important they are to the overall slip budget of this part of the fault zone, and therefore how likely these kind of hazard scenarios are, and make this an important question to study. Significant fault creep occurs from near Highway 46 south of Parkfield all the way north of San Juan Bautista. But to date, there have only been a handful of attempts to study paleoseismicity in this part of the San Andreas. In the 1980s, on the north and south ends of the creeping section, there were slip rate studies, which these studies corroborated the slip rates which were beginning to be documented by creep meters, and showed that over the Holocene, the geologic slip rates were quite similar. Then in the 2000s, there was my work at Parkfield at the Miller's Field site, and then the Fluke Ranch site in the heart of the creeping section. We'll look at these briefly. And then I'll also show you results from the Dry Lake Valley site, which is not far from the work that we're going to hear about next from Vel Filibisian at the Topo Creek site. I was fortunate to join the response to the 2004 earthquake with Ramon, where we were able to observe and document what the ground deformation looked like in that earthquake. And basically, it was a network of left-stepping ground cracks, closely following the geomorphic expression of fault scars at the site. Individual cracks extended for several meters, typically, and as much as 10 meters, and they commented just a few centimeters of displacement across them at the surface. Interestingly, we saw in this image in the middle that during the 2013 to 2014 historic drought in Central California, similar types of ground cracks, but a little different on the central creeping section of the fault. Here it had literally not rained appreciably for more than a year, and the dry clayey soils acted like a clay model, experiencing right lateral deformation, accumulating opening mode ground cracks, which stepped left and formed crack sets along the fault trace. And we'll look at these a little bit more here. So in 2014, Michael Bunz and I documented these using structure from motion and ground-based photography and drone flights. And we saw these cracks at both the Dry Lake Valley Paleoseismic Site, which I'll show you momentarily, as well as the DeRose Winery, another place that we stopped. These are quite similar to some of the ground cracks that you might see if you drove through the creeping section and stopped along the road where the fault crosses through the road and the road is being kind of slowly ripped apart. The table here compares the cracks we observed in the trenches on the left with the ones that were climatically modulated and we observed in 2014, and the center, and on the right, the Parkfield ground cracks. The ones in the center, the creep-induced ground crack deformation structures, consisted of small, tens of centimeters to just over a meter long opening mode cracks, which are oriented about 30 to 50 degrees, rotated counterclockwise of the fault trace. These tension cracks were left stepping and organized into crack sets which were oriented about 10 to 20 degrees clockwise, also clockwise from the San Andreas fault trace. And these crack sets extended for 5 to 10 meters before stepping left into another crack set. We infer that the crack sets are similar to Rydell shears that form during fault zone ruptures. Overall, the width of the deformation zone was fairly narrow, just a few meters wide. And within these trenches, that we're going to see at Dry Lake Valley show that faulting is also expressed as clockwise oblique cracking. And what we observed at Dry Lake Valley was that the crack orientations were kind of more on the opening mode rotational scheme of what we saw in 2014. And in 2004 at Parkfield, these cracks were a little bit different. They were also rotated clockwise, oblique to the San Andreas fault and left stepping, but they generally were longer, up to 10 meters in places, and they weren't just opening mode. They also had right lateral slip across them, and they were less oblique overall. So kind of maybe a mix of opening and right lateral cracks. So over time, because of fault creep and these moderate magnitude ground deformations, we can produce a lot of the evidence used to infer earthquake histories in paleoseismic trenches elsewhere. So a lot of things that we use at those sites are not necessarily diagnostic of large surface rupturing earthquakes. There's probably just two good pieces of evidence for large ruptures in a creeping environment: large fissures and large free face fault scarps in a vertical sense forming along and basically having a large displacement or opening where pieces of the fault scarp or the fissure are falling in and being buried intact within the fault zone stratigraphy. To be more clear, we do believe that fissures and fault scarp derived colluvium do occur with creeping faults, but these are going to look a lot more like what we see on the bottom images here. Fissures will be narrow. The fissure orientation will likely be oblique to the fault trace, these opening mode cracks, and filled primarily with fines from the surface, from dust and soil horizon material falling in, and in a very grain by grain manner. Similarly, colluvium shed across the fault scarp with a vertical sense of slip will be shed in a diffusive manner, accumulating mostly soil A horizon material, forming a dark colluvial mass on the downthrown side. So let's tour some of these paleoseismic trench exposures that have been conducted on the central San Andreas fault. Here's some from the Miller's Field site, which we investigated in 2004 and 2007, digging trenches across a sag depression and a small pressure ridge. Here the faults also are branched towards the surface from the main fault traces, with ground cracking observed all the way into the modern soils. Additionally, across the areas with a component of vertical deformation, we observed that the downthrown sides of the fault was infilled with dark soil, looking much like soil A horizon material, presumably from that grain by grain colluvial deposition across the fault scarp as one side moved up and the other down. The steady diffusion of materials consistent with creep and not rupture. And we also observed that many of the fault surface traces were actually oriented oblique to the geomorphic fault trace, much like the ground cracking in 2004 at Parkfield, and also what we observed in the creeping section in 2014 from the climatic creep rupture. Here's the Fluke Ranch site of Cashman et al. 2007. This figures are available from their supplemental online material. Beautifully documented trench with nice stratigraphy. They saw a lot of this upward branching faults coming to the surface. But no evidence of large ruptures were observed. In fact, this site is famous because of what they did in a microscopic sense. They collected the shear bands of the sands and silts in an in situ manner and looked at those under the microscope and compared those with parts of the San Andreas fault which are known to have experienced rupture. And what they saw is that the areas that had experienced rupture, the sand and silt grains in the fault zone had a cataclasic fracturing in them. And this was not observed here on the creeping section of this Fluke Ranch site. Those faults that they sampled, the grains were all intact and clearly had been rotated and into the fault zone in a very slow manner that didn't fracture them. Here's the Dry Lake Valley site. Near the heart of the creeping section. We targeted this area because of the relatively recent depositional environments and steep fault scarps there that suggested to us if there was a large rupture that we might be able to see significant ground deformation that would preserve that. We investigated a total of 9 different trenches. I'll just show you a few of them briefly. Here we're looking at T4 on the right, and hopefully the main thing you see in this image is that there's kind of 2 contrasting units. There's like this uplifted old pre-sag fan stratigraphy that's kind of more brown, and more gray and dark cumulate colluvial mass graded to sag fill on the right. And so again, this seems like the fault is expressed by grain uplift and diffusion across the fault scarp, consistent with creep. In our first field season in 2012, we really focused in on this trench 1, which was massive, crossing the entire sag pond, and had a wide expression of faulting on both sides of it. On the southwest side, it had the best preserved stratigraphy, and on the northwest side of the fault, there was really well-preserved fracturing within the trench walls, although the stratigraphy was less exciting to look at. Oblique ground cracking was prevalent across the trench. Like we saw these opening mode cracks at the surface in 2014, we saw them in the trench at Dry Lake Valley. This was really pronounced on the northeast side of the trench, and you can see it here on the trench wall photo, kind of depicted there. And then on the right lower image, you can see actually the cracks preserved in the floor of the trench. It was a really dusty environment, so that took a lot of cleaning to preserve and show that, but you get a sense of kind of the width of these opening cracks and what they're filled with in that image. The shear zone on the southwest side of the trench really got us thinking about the possibility of evidence supporting major ground rupture because of the presence of these really large clasts found in the fault zone that kind of like felt almost like they were in a fissure, but with excavation of a fault parallel trench, we realized that at some point a channel had crossed through the fault zone, and the presence of these boulders was really related to original deposition and possibly reworking by shear over the last thousands of years as well. So not really good evidence of large ruptures. Here's a logging interpretation of Trench 7 along with a photo mosaic. The one thing I want to point you to here is these narrow little cracks which extend for 50 centimeters to a meter and are buried. And so these filled fissures start to make us think about the potential for large ruptures being preserved here at some point in the past. If that was true, this would have occurred sometime after 1779 AD. But these are actually not that big in the end. The filled fissures are only open 3, 4, 5 centimeters. It's not a massively open thing. We don't have those sidewall stratigraphic blocks infilling them. And so these could have formed during periods of more extreme dryness, like we saw in 2014, perhaps an even drier period in the past. At Dry Lake Valley, that weak evidence for somewhat larger ground deformation, about 800 to maybe a little younger, maybe 1,000 years before present, aligns with a time period when there were earthquakes to the south and north of the creeping section. So maybe this is a period to hone in on and look for more evidence somewhere else along the creeping section, but this is clearly not definitive information about earthquakes. I would argue that other areas of time on this diagram are probably better to focus in on, which would be about between 1500 AD and 1715 AD, when there was a lot of rupture activity to both the north and south of the creeping section on the San Andreas. This would be an area to look for earthquakes coming into the creeping section for sure, and also because of climate. That earlier period at Dry Lake Valley between 1780 and 1031 AD actually coincides with the medieval dry climate anomaly, which was much drier than what we experienced in 2014. It's associated with major low stands of lakes in the region, hugely decreased pollen counts in many cores, and huge changes in terms of human dynamics with violence, and so huge extreme drought period. And so ground cracking is likely prominently likely to be occurring in the creeping section of the San Andreas, perhaps without even rupture occurring. Whereas this target time period, maybe more in the 1500 to 1750 time, would be better to look at because this was actually a relatively wet period of time in California's history, and also had a lot of large earthquakes. And so more likely, if there's presence of large ground cracking, it's more likely due to earthquakes. Additional approaches moving forward, I would argue that we should consider the following. Look at structures off of the main San Andreas fault trace. Presumably, a large rupture would activate many of the secondary fault traces adjacent to the primary fault trace along the San Andreas fault. And these traces won't have as much deformation from creep, so that perhaps will not confuse us as much when looking in the trench. And then implementing microstructural analysis, as was done by Cashman et al. 2007, is also another way to go, but here we'd be hunting for evidence of grain cladoclasis in as many fault traces as we could look at. Potentially looking at major discrete lateral channel offsets could be another way to go, as was described in Rockwell and Meltzner 2008 in Southern California's creeping areas. And finally, I kind of wonder if there's some other way to look at broader scale geomorphology to look for major events that could have left their mark on the landscape through drainage basin reorganizations, etc. But definitely ideas 1 and 2, along with that narrow time span of 1500 to 1750, would be probably where I'd look next paleoseismically. So thank you.